If it's
Do we have to be very
It clearly says feet. Don't yell at me that you didn't read carefully.
We have to be
Get ready, Anna.
I don't know how to convert feet.
I don't know either. But I do know how to go feet into inches and inches into centimeters.
Oh my god.
why don't you just divide by 3.3 or whatever? Isn't it 3.1 something maybe? Is that what the conversion between meters and
Yeah, nope. I'm just waiting for him to get.
because there's like a little more than a yard in the what?
Talk about the secret on the video. On the YouTube video.
Oh, Mary Grace.
Editing. I hate doing editing. Yes, 57.9. Alright. Ooh, that's kilowatts. That's gotta be watts.
I didn't do that.
It's not gonna be that much more. I don't think it's much power.
1021 2.
It's kind of a lot. Yeah, it's a lot.
I ballpark now. Oh, no, but I guess I took 57.
That's actually 100,000.
Yeah, 100,000, 2,000 liters per second.
Yep.
Yeah.
Yep.
So it's a
50,000 like 2-liter soda bottles per second.
Oh, that's.
I can almost visualize that. Not so huge that I can't even imagine.
I kind of visualize the soda like in the bottles.
All right, come on, right? One example for me, one example on your own. We're good. We're good. All right, so we do not have 2 videos that I want to watch. If you'd like to watch, I think one of the videos is really more construction oriented and kind of what it takes to put in our upstream reservoir for the plant. One of the videos kind of, I think, you know what, let's take a very quick look at the first one because I want you to see what the turbines look like. I'm pretty sure this first video gives us a glimpse of one of the turbines. Oh no, this is the other one. I don't even care about volume. I don't. Yeah, this might show us a turbine. Yeah, I think it's camera.
Are we supposed to be able to hear this or no?
I don't really care about the volume. Right. So they want to put a hydroelectric plant here. I think this is an abandoned quarry, right? So this used to be like an open pit mine for something. So now they're going to turn that into the reservoir of a hydroelectric plant. Which is kind of smart. Maybe you have a kind of fake lake sitting there. Not so
Intelligent energy.
Yeah, this is like a advertising.
And people can't swim in it.
They're not going to show us turbines. Yeah,
I
they're
would
not
want
going
to
to
get
show us.
some
Yeah. All right, sorry.
That's okay.
All right. So yeah, no time permitting to do any more watching than that. So that closes out hydroelectric. I think we had already talked about advantages and disadvantages. I don't really have any new thoughts about it. Yeah, we definitely talked about those last time. All right. So we have about 10 minutes to begin talking about wind power. Now the good news about wind power is there is an equation for it in the data booklet. We actually haven't looked at the data booklet yet in topic 8. So we have 3 objectives. One is to outline the basic features of a wind generator. We will certainly finish that today with ease. We do want to determine the power that can be delivered by a wind generator, assuming that all of the wind kinetic energy is converted into turbine kinetic energy. But then we also need to explain why that's impossible. And then we do want to be able to solve problems, quantitative problems involving wind power. So the wind generator is the simplest, right? Hydroelectric was the second simplest in terms of schematics. For the wind generator, all we need is the turbine and the generator, and that's it. Right, that's it. So the turbine is right up here. The generator is typically underground, or at least on the ground. The generator is not usually in the nacelle of the turbine itself. We turn the lights off so we can see the pictures down here better. Not much better. Typically the blades on these, there are almost always 3 blades, and they're usually very skinny. And these particular wind turbines are very close to the ground. Like ridiculously close to the ground. These things are usually quite high. Questions from anybody about the turbine and the generator? Yeah, Ian.
Is it like super efficient?
What's our input energy? So if the input energy is in fact the kinetic energy of the air molecules that are interacting with this disk of spinning blades, then no, it's not very efficient because the wind is still going to be moving very fast when it gets past the turbine. So no, but we might have some more discussing to do with that next time. But that's a great segue into what our energy conversion is. So it is in fact the kinetic energy of the air molecules, right? That is our starting energy, and then that will immediately get changed. Some of that kinetic energy will get changed into rotational kinetic energy of the turbine, right? And then just like all of our others, the rotational kinetic energy of the turbine changes to rotational kinetic energy of the generator, and then we get our electricity. So it's exactly the same thing as our hydroelectric, we just have a different fluid that's spinning the turbine. Instead of water molecules losing kinetic energy to the turbine, we have air molecules losing kinetic energy to the turbine. So let's look at an animation of that, and then we might have enough time to play a tiny bit to see if we can produce wind power here. Now, the IB objective specifically says we only need to know about horizontal axis wind turbines. There are kind of weirdo looking things, like this is a vertical axis wind turbine where we have these kind of curved things that would spin, this way. We don't care about that, right? These are the ones we care about. The horizontal axis, the axis of rotation is oriented parallel to the ground. So this is a pretty high density wind farm in California. But that's not what I wanted to look at. I wanted to look at this over here. All right, so here these green arrows are supposed to represent moving air molecules, right, that are incident on the turbine blades. The air molecules will give some of the kinetic energy up to the turbine blades, right, that starts spinning. So what does this say down here? When the blades turn, the rotor turns a shaft which transfers the motion into the nacelle. So the spinning turbine blades, right, will transfer that rotation inside the rest of the structure up here called the nacelle. We will have a gearbox that will increase the rotational speed. So these blades, they don't spin that fast. Right? They really don't. So we definitely need to utilize gear ratios to increase the rotational speed. And then actually this is showing that the generator is up here within the nacelle, so maybe I'm wrong, maybe that typically is the case. So we are generating our electrical current up here, and we can send that down to join up with the currents from other turbines, right? And then we can go ahead and distribute that through our power grid, right? And then maybe we can use that for a decent amount of our electrical needs, and maybe not. Maybe we can't. Yeah, hi.
The generator is like on the
Yes.
How would the rotation kinetic energy get to the generator?
Yeah, I mean, I think you could do it, but I think I was just wrong. And that we do have a generator up there. Yeah, I'm sure we can engineer a way to do that, but let's erase that model from our heads. All right, so how much power can these things produce? Well, the size in a couple of regards matters a lot. So the size of the turbine blade, the length of the turbine blade is hugely important because we can capture more air molecules, right? If we have, like, if I Hi, you alright? Okay. Right, if I'm going to be the turbine blades and my arms can catch, wind, if it's a windy day, right? Liam's arms can capture more energy from the wind because he has longer arms, where he can reach out and catch more air. So that's why longer turbine blades matter. And generally speaking, if we double the blade length, we'll get 4 times more power because we're talking about a circle. Right? Here's one turbine blade, here's another turbine blade, here's the other turbine blade. Right? Those are spinning, and that carves out a circle. So if we double the length of the turbine blade, we get a circle that has double the radius, and the total surface area of that circle goes with the radius squared. So we double the length, we can get 4 times the power. So that's one way that size matters. The other way is getting these things taller, getting them further off the ground. The reason that generates more power is we have more wind up there. We go higher up, we have more wind. How come? We don't go that high into the jet stream. Yeah.
Less obstacles.
Yeah, less friction, right? We have wind hitting the school, we have wind hitting trees. That takes a lot of kinetic energy out of the air molecules. If we can get above the surrounding stuff, trees, roots, all that stuff, we'll have faster winds, right? Yeah, that's probably going to be the most logical stopping point instead of cramming this next thing in. So how many of you am I gonna not see on Monday? Quite a few. So I definitely will do my best to videotape